Hello viewers, welcome to my channel Online Biology Tutorials. Let's start with the audio of Chapter 11. Electricity. Electricity has an important place in modern society. It is a controllable and convenient form of energy for a variety of uses in homes, schools, hospitals, industries, and so on. What constitutes electricity? How does it flow in an electric circuit? What are the factors that control or regulate the current through an electric circuit? In this chapter we shall attempt to answer such questions. We shall also discuss the heating effect of electric current and its applications. 11.1 Electric current and circuit. We are familiar with air current and water current. We know that flowing water constitute water current in rivers. Similarly, if the electric charge flows through a conductor, for example through a metallic wire, we say that there is an electric current in the conductor. In a torch we know that the cells or a battery, when placed in proper order, provide flow of charges or an electric current through the torch bulb to glow. We have also seen that the torch gives light only when its switch is on. What does a switch do? A switch makes a conducting link between the cell and the bulb. A continuous and closed path of an electric current is called an electric circuit. Now, if the circuit is broken anywhere or the switch of the torch is turned off, the current stops flowing and the bulb does not glow. How do we express electric current? Electric current is expressed by the amount of charge flowing through a particular area in unit time. In other words, it is the rate of flow of electric charges. In circuits using metallic wires, electrons constitute the flow of charges. However, electrons were not known at the time when the phenomenon of electricity was first observed. So, electric current was considered to be the flow of positive charges, and the direction of flow of positive charges was taken to be the direction of electric current. Conventionally, in an electric circuit, the direction of electric current is taken as opposite to the direction of the flow of electrons, which are negative charges. If a net charge Q flows across any cross-section of a conductor in time t, then the current I through the cross-section is I is equal to Q by T. The SI unit of electric charge is Coulomb C, which is equivalent to the charge contained in nearly 6 into 10 to the power 18 electrons. We know that an electron possesses a negative charge of 1.6 into 10 to the power minus 19 C. The electric current is expressed by a unit called ampere K, named after the
French scientist André Marie Ampère, 1775 til 1836.
1 ampere is constituted by the flow of 1 coulomb of charge per second, that is, 1A equals 1C/1S. Small quantities of current are expressed in milliampere. 1 milliampere equals 10 to the power minus 3A, or in microampere, 1 microA equals 10 to the power minus 6A. An instrument called ammeter measures electric current in a circuit. It is always connected in series in a circuit through which the current is to be measured. Figure 11.1 shows the schematic diagram of a typical electric circuit comprising a cell, an electric bulb, an ammeter, and a plug key. Note that the electric current flows in the circuit from the positive terminal of the cell to the negative terminal of the cell through the bulb and ammeter. Example 11.1. A current of 0.5 A is drawn by a filament of an electric bulb for 10 minutes. Find the amount of electric charge that flows through the circuit. Solution. We are given I equals 0.5 A. T equals 10 minutes equals 600 S. From equation 11.1, we have Q is equal to IT equals 0.5 A into 600 S equals 300 C. Questions. What does an electric circuit mean? 2. Define the unit of current. 3. Calculate the number of electrons constituting 1 coulomb of charge. 11.2 Electric potential and potential difference. What makes the electric charge to flow? Let us consider the analogy of flow of water. Charges do not flow in a copper wire by themselves, just as water in a perfectly horizontal tube does not flow. If one end of the tube is connected to a tank of water kept at a higher level, such that there is a pressure difference between the two ends of the tube, water flows out of the other end of the tube. For flow of charges in a conducting metallic wire, the gravity, of course, has no role to play. The electrons move only. If there is a difference of electric pressure, called the potential difference, along the conductor, this difference of potential may be produced by a battery consisting of one or more electric cells. The chemical action within a cell generates the potential difference across the terminals of the cell, even when no current is drawn from it. When the cell is connected to a conducting circuit element, the potential difference sets the charges in motion in the conductor and produces an electric current. In order to maintain the current in a given electric circuit, the cell has to expend its chemical energy stored in it. We define the electric potential difference between 2 points in an electric circuit carrying some current as the work done to move a unit charge from one point to the other. Potential difference V between 2 points equals work done W/charge Q. V is equal to W upon Q. The SI unit of electric potential difference is volt V, named after Alessandro Volta, 1745 to 1827, an Italian physicist. 1 volt is the potential difference between 2 points in a current-carrying conductor. When 1 joule of work is done to move a charge of 1 coulomb from one point to the other, therefore 1 volt equals 1 joule upon 1 coulomb. The potential difference is measured by means of an instrument called the voltmeter. The voltmeter is always connected in parallel across the points between which the potential difference is to be measured. Example 11.2. How much work is done in moving a charge of 2C across 2 points, having a potential difference 12V? Solution. The amount of charge Q that flows between 2 points at potential difference V equals 12V is 2C. Thus, the amount of work W done in moving the charge from equation 11.2 is
Wrówna się VQ
equals 12V into 2C equals 24J. Questions. Name a device that helps to maintain a potential difference across a conductor. 2. What is meant by saying that the potential difference between 2 points is 1V? 3. How much energy is given to each coulomb of charge passing through a 6V battery? 11.3 Circuit diagram. We know that an electric circuit, as shown in figure 11.1, comprises a cell, or a battery, a plug, key, electrical components, and connecting wires. It is often convenient to draw a schematic diagram in which different components of the circuit are represented by the symbols conveniently used. Conventional symbols used to represent some of the most commonly used electrical components are given in Table 11.1. 11.4 Ohm's law. Is there a relationship between the potential difference across a conductor and the current through it? Let us explore with an activity. Activity 11.1. N. Set up a circuit as shown in figure 11.2, consisting of a nichrome wire XY of length, say 0.5 m, an ammeter, a voltmeter, and 4 cells of 1.5 V each. Nichrome is an alloy of nickel, chromium, manganese, and iron metals. And first use only 1 cell as the source in the circuit. Note the reading in the ammeter I for the current and reading of the voltmeter, V for the potential difference across the nichrome wire XY in the circuit. Tabulate them in the table given. And next connect 2 cells in the circuit and note the respective readings of the ammeter and voltmeter for the values of current through the nichrome wire and potential difference across the nichrome wire. And repeat the above steps using 3 cells and then 4 cells in the circuit separately. And calculate the ratio of V to I for each pair of potential difference V and current I. Plot a graph between V and I, and observe the nature of the graph. In this activity, you will find that approximately the same value for V/I is obtained in each case. Thus, the VI graph is a straight line that passes through the origin of the graph, as shown in figure 11.3. Thus, V/I is a constant ratio. In 1827, a German physicist, George Simon Ohm, 1787 to 1854, found out the relationship between the current I flowing in a metallic wire and the potential difference across its terminals. The potential difference V across the ends of a given metallic wire in an electric circuit is directly proportional to the current flowing through it, provided its temperature remains the same. This is called Ohm's law. In other words, V is directly proportional to I. V upon I is a constant. V is equal to IR, a given temperature, and is called its resistance. It is the property of a conductor to resist the flow of charges through it. SI. Unit is ohm, represented by the Greek letter omega. According to Ohm's law, R is equal to V divided by I. If the potential difference across the two ends of a conductor is 1V, and the current through it is 1A, then the resistance R of the conductor is 1 ohm. That is, 1 ohm equals 1 volt divided by 1 ampere. Also from equation 11.5 we get I is equal to V by R. It is obvious from equation 11.7 that the current through a resistor is inversely proportional to its resistance. If the resistance is doubled, the current gets halved. In many practical cases, it is necessary to increase or decrease the current in an electric circuit. A component used to regulate current without changing the voltage source is called variable resistance. In an electric circuit, a device called rheostat is often used to change the resistance in the circuit. We will now study about electrical resistance of a conductor with the help of following activity. Activity 11.2. N. Take a nichrome wire, a torch bulb, a 10W bulb, and an ammeter 0 to 5A range, a plug, key, and some connecting wires. N. Set up the circuit by connecting 4 dry cells of 1.5 V each in series with the ammeter, leaving a gap XY in the circuit, as shown in figure 11.4. Complete the circuit by connecting the nichrome wire in the gap XY. Plug the key. Note: down the ammeter reading. Take out the key from the plug. Note: always take out the key from the plug after measuring the current through the circuit. N. Replace the nichrome wire with the torch bulb in the circuit and find the current through it by measuring the reading of the ammeter. And now repeat the above step with the 10W bulb in the gap XY. N. Are the ammeter readings different for different components connected in the gap XY? What do the above observations indicate? And you may repeat this activity by keeping any material component in the gap. Observe the ammeter readings in each case. Analyze the observations. In this activity, we observe that the current is different for different components. Why do they differ? Certain components offer an easy path for the flow of electric current while the others resist the flow. We know that motion of electrons in an electric circuit constitutes an electric current. The electrons, however, are not completely free to move within a conductor. They are restrained by the attraction of the atoms among which they move. Thus, motion of electrons through a conductor is retarded by its resistance. A component of a given size that offers a low resistance is a good conductor. A conductor having some appreciable resistance is called a resistor. A component of identical size that offers a higher resistance is a poor conductor. An insulator of the same size offers even higher resistance. 11.5 Factors on which the resistance of a conductor depends. Activity 11.3. N. Complete an electric circuit consisting of a cell, an ammeter, a nichrome wire of length L, say marked 1, and a plug key as shown in figure 11.5. Now plug the key. Note the current in the ammeter. N. Replace the nichrome wire by another nichrome wire of same thickness but twice the length, that is 2L marked 2, in the figure 11.5. N. Note the ammeter reading. N. Now replace the wire by a thicker nichrome wire of the same length L marked 3. A thicker wire has a larger cross-sectional area. Again, note down the current through the circuit. N. Instead of taking a nichrome wire, connect a copper wire marked 4. In figure 11.5 in the circuit, let the wire be of the same length and same area of cross-section as that of the first nichrome wire marked 1. Note the value of the current, and notice the difference in the current in all cases. And does the current depend on the length of the conductor? And does the current depend on the area of cross-section of the wire used? It is observed that the ammeter reading decreases to 1/2 when the length of the wire is doubled. The ammeter reading is increased when a thicker wire of the same material and of the same length is used in the circuit. A change in ammeter reading is observed when a wire of different Material of the same length and the same area of cross-section is used. On applying Ohm's law X 11.5, 11.7, we observe that the resistance of the conductor depends I on its length, 2 on its area of cross-section, and 3 on the nature of its material. Precise measurements have shown that resistance of a uniform metallic conductor is directly proportional to its length L and inversely proportional to the area of cross-section A. That is, R is directly proportional to L, and R is directly proportional to 1 by A. Thus, combining both, R is directly proportional to L by A, or R is equal to rho L by A, where rho is a constant of proportionality and is called the electrical resistivity of the material of the conductor. The SI unit of resistivity is ohm. It is a characteristic property of the material. The metals and alloys have very low resistivity in the range of 10 to the power minus 8 ohm to 10 to the power minus 6 ohm. They are good conductors of electricity. Insulators like rubber and glass have resistivity of the order of 10 to the power 12 to 10 to the power 17 ohm. Both the resistance and resistivity of a material vary with temperature. Table 11.2 reveals that the resistivity of an alloy is generally higher than that of its constituent metals. Alloys do not oxidize, burn, readily at high temperatures. For this reason, they are commonly used in electrical heating devices like electric iron, toasters, etc. Tungsten is used almost exclusively for filaments of electric bulbs, whereas copper and aluminium are generally used for electrical transmission lines. Example 11.3. A. How much current will an electric bulb draw from a 220 V source if the resistance of the bulb filament is 1200 ohm? B. How much current will an electric heater coil draw from a 220 V source if the resistance of the heater coil is 100 ohm? Solution. A. We are given V equals 220 V. R equals 1200 ohm. From equation 12.6, we have the current I equals 220 V / 1200 ohm equals 0.18 A. B. We are given V equals 220 V, R equals 100 ohm. From equation 11.6, we have the current I equals 220 V / 100 ohm equals 2.2 A. Note the difference of current drawn by an electric bulb and electric heater from the same 220 V source. Example 11.4. The potential difference between the terminals of an electric heater is 60 V when it draws a current of 4 A from the source. What current will the heater draw if the potential difference is increased to 120 V? Solution. Kindly check the solution from the book. Example 11.5. Resistance of a metal wire of length 1 m is 26 ohms at 20 degrees Celsius. The diameter of the wire is 0.3 millimeters. What will be the resistivity of the metal at that temperature? Using table 11.2, predict the material of the wire. Solution. Kindly check the solution from the book. Example 11.6. A wire of given material having length L and area of cross-section A has a resistance of 4 ohm. What would be the resistance of another wire of the same material having length L/2 and area of cross-section 2A? Solution. Kindly check the solution from the book. Questions. 1. On what factors does the resistance of a conductor depend? 2. Will current flow more easily through a thick wire or a thin wire of the same material when connected to the same source? Why? 3. Let the resistance of an electrical component remains constant while the potential difference across the two ends of the component decreases to half of its former value. What change will occur in the current through it? 4. Why are coils of electric toasters and electric irons made of an alloy rather than a pure metal? 5. Use the data in table 11.2 to answer the following. Which among iron and mercury is a better conductor? B. Which material is the best conductor? 11.6 Resistance of a system of resistors. In preceding sections, we learned about some simple electric circuits. We have noticed how the current through a conductor depends upon its resistance and the potential difference across its ends. In various electrical gadgets, we often use resistors in various combinations. We now, therefore, intend to see how Ohm's law can be applied to combinations of resistors. There are two methods of joining the resistors together. Figure 11.6 shows an electric circuit in which three resistors having resistances R1, R2 and R3 respectively are joined end to end. Here the resistors are said to be connected in series. Figure 11.7 shows a combination of resistors in which three resistors are connected together between points X and Y. Here the resistors are said to be connected in parallel. 1.6.1 resistors in series. What happens to the value of current when a number of resistors are connected in series in a circuit? What would be their equivalent resistance? Let us try to understand these with the help of the following activities. Activity 11.4. N. Join three resistors of different values in series. Connect them with a battery, an ammeter and a plug key, as shown in figure 11.6. You may use the resistors of values like 1 ohms, 2 ohms, 3 ohms, etc., and a battery of 6V for performing this activity. N. Plug the key. Note the ammeter reading. N. Change the position of ammeter to anywhere in between the resistors. Note the ammeter reading each time. N. Do you find any change in the value of current through the ammeter? You will observe that the value of the current in the ammeter is the same independent of its position in the electric circuit. Means that in a series combination of resistors the current is the same in every part of the circuit or the same current through each resistor. Activity 11.5. N. In activity 11.4, insert a voltmeter across the ends X and Y of the series combination of three resistors, as shown in figure 11.6. N. Plug the key in the circuit and note the voltmeter reading. Gives the potential difference across the series combination of resistors. Let it be V. Now measure the potential difference across the two terminals of the battery. Compare the two values. N. Take out the plug key and disconnect the voltmeter. Now insert the voltmeter across the ends X and P of the first resistor, as shown in figure 11.8. Plug the key and measure the potential difference across the first resistor. Let it be V1. And similarly, measure the potential difference across the other two resistors separately. Let these values be V2 and V3 respectively. And deduce a relationship between V1, V2 and V3. You will observe that the potential difference V is equal to the sum of potential differences V1, V2 and V3. That is the total potential difference across a combination of resistors in series is equal to the sum of potential difference across the individual resistors. That is, V equals V1 plus V2 plus V3. In the electric circuit shown in figure 11.8, let I be the current through the circuit. The current through each resistor is also I. It is possible to replace the three resistors joined in series by an equivalent single resistor of resistance R such that the potential difference V across it and the current I through the circuit remains the same. Applying the Ohm's law to the entire circuit, we have V equals IR. On applying Ohm's law to the three resistors separately, we further have V1 equals IR1, V2 equals IR2, and V3 equals IR3.
IR är lik med IR1 och IR2 och IR3.
Or RS equals R1 plus R2 plus R3. We can conclude that when several resistors are joined in series, the resistance of the combination RS equals the sum of their individual resistances R1, R2, R3, and is thus greater than any individual resistance. Example 11.7. An electric lamp, whose resistance is 20 ohm, and a conductor of 4 ohm resistance are connected to a 6V battery. Figure 11.9. Calculate the total resistance of the circuit, B, the current through the circuit, and C, the potential difference across the electric lamp and conductor. Solution can be checked from the book. Questions. Draw a schematic diagram of a circuit consisting of a battery of 3 cells of 2V each, a 5 ohm resistor, an 8 ohm resistor, and a 12 ohm resistor, and a plug key all connected in series. 2. Redraw the circuit of question 1, putting in an ammeter to measure the current through the resistors and a voltmeter to measure the Potential difference across the 12 ohm resistor. What would be the readings? In the ammeter and the voltmeter? 1.6.2 resistors in parallel. Now let us consider the arrangement of 3 resistors joined in parallel, with a combination of cells or a battery, as shown in figure 11.7. Activity 11.6. Make a parallel combination XY of 3 resistors having resistances R1, R2, and R3, respectively. Connect it with a battery, a plug key, and an ammeter as shown in figure 11.10. Also connect a voltmeter in parallel with the combination of resistors. Plug the key and note the ammeter reading. Let the current be I. Also take the voltmeter reading. It gives the potential difference V. Cross the combination. The potential difference across each resistor is also V. This can be checked by connecting the voltmeter across each individual resistor. See figure 11.11. Take out the plug from the key. Remove the ammeter and voltmeter from the circuit. Insert the ammeter in series with the resistor R1, as shown in figure 11.11. Note the ammeter reading I1. Similarly, measure the currents through R2 and R3. Let these be I2 and I3 respectively. What is the relationship between I1, I2, and I3? It is observed that the total current I is equal to the sum of the separate currents through each branch of the combination. I equals I1 plus I2 plus I3. 11.15. Let Rp be the equivalent resistance of the parallel combination of resistors. By applying Ohm's law to the parallel combination of resistors, we have I equals V by Rp. 11.16. On applying Ohm's law to each resistor, we have I1 equals V by R1, I2 equals V by R2, and I3 equals V by R3. 11.17. From X 11.15 to 11.17, we have V by Rp equals V by R1 plus V by R2 plus V by R3, or 1 by Rp equals 1 by R1 plus 1 by R2 plus 1 by R3. Thus, we may conclude that the reciprocal of the equivalent resistance of a group of resistances joined in parallel is equal to the sum of the reciprocals of the individual resistances. Example 11.8. In the circuit diagram given in figure 11.10, suppose the resistors R1, R2 and R3 have the values 5 ohm, 10 ohm, 30 ohm respectively, which have been connected to a battery of 12 V. Calculate A, the current through each resistor, B, the total current in the circuit, and C, the total circuit resistance. Solution can be seen from the book. Example 11.9. If in figure 11.12 R1 equals 10 ohm, R2 equals 40 ohm, R3 equals 30 ohm, R4 equals 20 ohm, R5 equals 60 ohm, and a 12 V battery is connected to the arrangement, calculate A, the total resistance in the circuit, and B, the total current flowing in the circuit. Solution can be seen from the book. We have seen that in a series circuit the current is constant throughout the electric circuit. Thus it is obviously impracticable to connect an electric bulb and an electric heater in series because they need currents of widely different values to operate properly. See example 11.3. Another major disadvantage of a series circuit is that when one component fails, the circuit is broken and none of the components works. If you have used fairy lights to decorate buildings on festivals, on marriage celebrations, etc., you might have seen the electrician spending a lot of time and trouble locating and replacing the dead bulb each has to be tested to find which has fused or gone. On the other hand, a parallel circuit divides the current through the electrical gadgets. The total resistance in a parallel circuit is decreased as per equation 11.18. This is helpful particularly when each gadget has different resistance and requires different current to operate properly. Questions. Judge the equivalent resistance when the following are connected in parallel: 1 ohm and 106 ohm, B 1 ohm and 103 ohm, and 106 ohm. 2. An electric lamp of 100 ohm, a toaster of resistance 50 ohm, and a water filter of resistance 500 ohm are connected in parallel to a 220 V source. What is the resistance of an electric iron connected to the same source that takes as much current as all three appliances, and what is the Current through it? 3. What are the advantages of connecting electrical devices in parallel with the battery instead of connecting them in series? 4. How can 3 resistors of resistances 2 ohm, 3 ohm, and 6 ohm be connected to give a total resistance of A 4 ohm, B 1 ohm? 5. What is A the highest, B the lowest total resistance that can be secured by combinations of 4 coils of resistance 4 ohm, 8 ohm, 12 ohm, 24 ohm? 11.7 Heating effect of electric current. We know that a battery or a cell is a source of electrical energy. The chemical reaction within the cell generates the potential difference between its 2 terminals that sets the electrons in motion to flow the current through a resistor or a system of resistors connected to the battery. We have also seen in section 11.2 that to maintain the current, the source has to keep expending its energy. Where does this energy go? Part of the source energy in maintaining the current may be consumed into useful work like in rotating the blades of an electric fan. Rest of the source energy may be expended in heat to raise the temperature of gadget. We often observe this in our everyday life. For example, an electric fan becomes warm if used continuously for longer time, etc. On the other hand, if the electric circuit is purely resistive, that is, a configuration of resistors only connected to a battery, the source energy continually gets dissipated entirely in the form of heat. This is known as the heating effect of electric current. This effect is utilized in devices such as electric heater, electric iron, etc. Consider a current I flowing through a resistor of resistance R. Let the potential difference across it be V. Figure 11.13. Let T be the time during which a charge Q flows across. The work done in moving the charge Q through a potential difference V is VQ. Therefore, the source must supply energy equal to VQ in time T. Hence, the power input to the circuit by the sources P is equal to VQ by T, or the energy supplied to the circuit by the source in time T is PT. That is VIT. What happens to this energy expended by the source? This energy gets dissipated in the resistor as heat. Thus, for a steady current I, the amount of heat H produced in time T is
H égale V.
Applying Ohm's law equation 11.5, we get H equals I2RT. This is known as Joule's law of heating. The law implies that heat produced in a resistor is I directly proportional to the square of current for a given resistance, 2 directly proportional to resistance for a given current, and 3 directly proportional to the time for which the current flows through the resistor. In practical situations, when an electric appliance is connected to a known voltage source, equation 11.21 is used after calculating the current through it using the relation I equals V/R. Example 11.10. An electric iron consumes energy at a rate of 840 W when heating is at the maximum rate and 360 W when the heating is at the minimum. The voltage is 220 V. What are the current and the resistance in each case? Solution can be seen from the book. Example 11.11. 100 J of heat is produced each second in a 4 ohms resistance. Find the potential difference across the resistor. Solution can be seen from the book. Questions. Why does the cord of an electric heater not glow while the heating element does? 2. Compute the heat generated while transferring 96,000 coulomb of charge in 1 hour through a potential difference of 50 V. 3. An electric iron of resistance 20 ohms takes a current of 5 A. Calculate the heat developed in 30s. 11.7.1 Practical applications of heating effect of electric current. The generation of heat in a conductor is an inevitable consequence of electric current. In many cases, it is undesirable as it converts useful electrical energy into heat. In electric circuits, the unavoidable heating can increase the temperature of the components and alter their properties. However, heating effect of electric current has many useful applications. The electric laundry iron, electric toaster, electric oven, electric kettle, and electric heater are some of the familiar devices based on Joule's heating. The electric heating is also used to produce light, as in an electric bulb. Here, the filament must retain as much of the heat generated as is possible so that it gets very hot and emits light. It must not melt at such high temperature. A strong metal with high melting point such as tungsten, melting point 3380 degrees Celsius, is used for making bulb filaments. The filament should be thermally isolated as much as possible, using insulating support, etc. The bulbs are usually filled with chemically inactive nitrogen and argon gases to prolong the life of filament. Most of the power consumed by the filament appears as heat, but a small part of it is in the form of light radiated. Another common application of Joule's heating is the fuse used in electric circuits. It protects circuits and appliances by stopping the flow of any unduly high electric current. The fuse is placed in series with the device. It consists of a piece of wire made of a metal or an alloy of appropriate melting point, for example aluminium, copper, iron, lead, etc. If a current larger than the specified value flows through the circuit, the temperature of the fuse wire increases. This melts the fuse wire and breaks the circuit. The fuse wire is usually encased in a cartridge of porcelain or similar material with metal ends. The fuses used for domestic purposes are rated as 1A, 2A, 3A, 5A, 10A, etc. For an electric iron, which consumes 1 kilowatt electric power when operated at 220 V, a current of 1000/220 A, that is, 4.54 A, will flow in the circuit. In this case, a 5A fuse must be used.
12.8 Electric power. You have studied in your earlier class that the rate of doing work is power. This is also the rate of consumption of energy. Equation 12.21 gives the rate at which electric energy is dissipated or consumed in an electric circuit. This is also termed as electric power. The power P is given by P is equals to VI, or P is equals to I square R is equals to V square by R. 12.22. The SI unit of electric power is watt, W. It is the power consumed by a device that carries 1 A of current when operated at a potential difference of 1 V. Thus, 1 W is equals to 1 volt into 1 ampere is equals to 1 VA. 12.23. The unit watt is very small. Therefore, in actual practice, we use a much larger unit called kilowatt. It is equal to 1000 watts. Since electrical energy is the product of power and time, the unit of electric energy is therefore watt-hour, WH. 1 watt-hour is the energy consumed when 1 watt of power is used for 1 hour. The commercial unit of electric energy is kilowatt-hour, kWh, commonly known as unit. 1 kWh is equals to 1000 watt into 3600 second is equals to 3.6 into 10 to the power 6 watt second is equals to 3.6 into 10 to the power 6 joule, J. More to know. Many people think that electrons are consumed in an electric circuit. This is wrong. We pay the electricity board or electric company to provide energy to move electrons through the electric gadgets like electric bulb, fan, and engines. We pay for the energy that we use. Example 12.12. An electric bulb is connected to a 220 volt generator. The current is 0.50 A. What is the power of the bulb? Solution. P is equals to VI. 220 volt into 0.50 A is equals to 110 joule per second is equals to 110 watt. Example 12.13. An electric refrigerator rated 400 watt operates 8 hours per day. What is the cost of the energy to operate it for 30 days at rupees 3 per kWh? Solution. The total energy consumed by the refrigerator in 30 days would be 400 W into 8 hours per day into 30 days is equals to 96,000 Wh or 96 kWh. Thus, the cost of energy to operate the refrigerator for 30 days is 96 kilowatt hour into rupees 3 per kWh is equals to rupees 288. Questions. 1. What determines the rate at which energy is delivered by a current? 2. An electric motor takes 5A from a 220 volt line. Determine the power of the motor and the energy consumed in 2 hours. What you have learned. A stream of electrons moving through a conductor constitutes an electric current. Conventionally, the direction of current is taken opposite to the direction of flow of electrons. The SI unit of electric current is ampere. To set the electrons in motion in an electric circuit, we use a cell or a battery. A cell generates a potential difference across its terminals. It is measured in volts V. Resistance is a property that resists the flow of electrons in a conductor. It controls the magnitude of the current. The SI unit of resistance is ohm. Ohm's law. The potential difference across the ends of a resistor is directly proportional to the current through it, provided its temperature remains the same. The resistance of a conductor depends directly on its length, inversely on its area of cross-section, and also on the material of the conductor. The equivalent resistance of several resistors in series is equal to the sum of their individual resistances. A set of resistors connected in parallel has an equivalent resistance Rp given by 1 upon Rp is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3 plus so on. The electrical energy dissipated in our resistor is given by W is equals to V into I into T. The unit of power is watt, W. 1 watt of power is consumed when 1A of current flows at a potential difference of 1V. The commercial unit of electrical energy is kilowatt hour, kWh. 1 kWh is equals to 3600,000 joule. It's equals to 3.6 into 10 to the power 6 joule.
So that's the end of the chapter. Hope every word I pronounced was clear to you. Hit like if this video was helpful to you. Subscribe and hit the bell icon for the recent updates. See you in the next video.